Hello everyone, it's almost 11 o'clock, so let's start. And I right now see that there are around 11 actively online right now, so I think that's a good number. Let's start it off. So, first of all, we are starting off a new venture. We have been trying it out for past few days with Vivek going live uh, to check out the platform, to check out how we can implement it, pros and cons, and uh, how well we can develop this further. So, in this session, this is one of the first sessions for real analysis. So far, we have been talking about algebra mostly. Hi, Indra and Krishna. So, in this particular class, I'll be talking about definition and examples of metric spaces. This is for absolute beginners. But unfortunately, turns out we teach this. Good morning, Krishna. So this is an absolute beginner class. Only prerequisite that you require is sets and functions. Two things that you have been learning since your school days. So one request: please feel free to stop me anytime you have a doubt. Leave a comment there, and I'll get back to you. And when it comes to the way we'll be handling the sessions, it'll be a little different from most of the coaching classes online. And I believe what I am saying right now is better quoted by I'm sorry is better quoted by Neil deGrasse Tyson, one of the famous astronomers of these days. He is famous not just for his astronomy. He is a science communicator. Science communication is a field where you speak science in a way that others can understand, the normal people can understand. So he has a quote in which he says, "Science literacy is not so much about what you know." That means learning science is not about how much you know, how much you have by heart concepts, but it's about how your brain is wired for thought. How well can you think science? How your brain is wired to ask questions? How well, given a new concept, how do you explore it? What questions do you ask to that concept so that you understand it better? So, our focus will not be in making you by heart the definition of metric spaces. I believe your schools and colleges have done that for you. We'll be focusing on understanding the definition. We'll be focusing on training ourselves to understand the definition better. One, we'll be focusing on training ourselves to understand applying these definition in different contexts. We'll explore a few examples and counterexamples, but through that, what we'll be focusing on is how will we construct examples and counterexamples ourselves. And then we'll do some challenges. There'll be some extra challenges. So this challenges and extra challenges section, you can always participate. The questions will be shown to you. You can always leave your thoughts in the comment section, and you can keep interacting with me there. So and then we'll look at some CSIR-NET questions, and you will see that these questions are not too hard. This will completely depend on the definition which we are going to discuss. And you'll see that these questions are not too hard. They're simply the concepts that we learn in our second BSc or third BSc. So, hi Nikita, welcome. So, and then I'll talk to you about maintaining a diary, something which helped me clear CSIR-NET back in December 2016. We'll also present some extra reading links which will help you search further into these topics. Now, why am I going to spend so much time? I believe I'll take somewhere around 2 to 3 hours. Today there will be 1 hour session, and in coming days we'll discuss further 2 to 3 hours to understand this topic. Why am I going to spend so much time on this symbol definition, which most probably your teachers taught in 5 minutes and walked off? The reason is this is one of the basic definitions. Hi Kessia, welcome. So this is one of the basic definitions which, when understood well, the other definitions which are made using this definition, as you know in real analysis, everything is built from scratch. Every single real analysis textbook that you know of start with one definition, and that one definition is definition of sets. From the every word which is used in that book will be defined well before it is used. So this is one of the crucial definitions, understanding of which is absolutely important. Once we reach CSIR-NET questions, welcome Joy. Once we reach CSIR-NET questions, you'll see why this definition is key and how at least 3 or 4 questions based on this definition is asked in each year's question in CSIR-NET. Let's start with definition and meaning. As I told you, to learn this definition, we simply need the definition of sets and functions. So set is something which is familiar to us. Let me recall 2 or 3 words related to functions which we will require for this definition. A function will have something called domain and codomain and range. Bartle and Sherbert, one of the best books for real analysis out there, talks about function. Imagine function as a machine where you put things into that machine, and this machine reworks that thing, reforms it into some other form and gives it out. For example, f of x is equal to x square. Put 3 into that machine, the machine works on it and gives you 9. So if you look at function as a machine, domain is all things which you are allowed to put into the function, and range is all possible form or numbers or whatever output you get from the function. And codomain is a set which contains this range set. Now, with these, which is known to all of us, we are ready to hit on definition of metric spaces. We need M to be a non-empty set. That's the only condition on the set M we are taking. Any non-empty set, it can contain anything. It can contain numbers, it can contain smileys, it can contain letters, whatever it is. A metric for M is a function. We are going to define a new function which we are going to denote by rho for the purpose of definition, and we'll call it a metric for M. This metric is particular for M, and this function should satisfy a couple of conditions. One, domain should be M, cross product. That's another definition that you would have learned soon just before defining functions in real analysis. 2, range should be contained in closed interval 0, infinity. Notice something very particular. Here, they have worded it very carefully, saying range contained in. It didn't say codomain should be 0, infinity, closed interval 0, infinity. It said range contained in closed interval 0, infinity. Not just these two, it should satisfy 4 more conditions. 1, rho of x, x is equal to 0 for all x belongs to M. Rho of x, y is greater than 0 for all x, y belongs to M. And x is not equal to y. Third condition, rho of x, y is equal to rho of y, x for all x, y belongs to M. Fourth condition says it's called triangle inequality, and that's very peculiar because we know what triangle is, and this has something to do with triangle, it seems. So it says rho of x, y is less than or equal to rho of x, z plus rho of z, y. Now, there are 6 conditions. Though we have numbered only 4, there are 6 conditions. And if rho satisfies these 6 conditions, we call rho, this particular function, a metric for M. And then the ordered pair M, rho is called a metric space. Note that I have taken this definition from Richard Goldberg's Methods of Real Analysis, and the definition which you learned in whichever book it is may be slightly different. So, but essentially, they will all mean the same. They'll carry the same meaning. Anyway, where did this definition come from? That's the most important part. Turns out this is a concept which we have been using since our school days. School, not even school, since the day we have been learning, we learned to walk when we were children, we have been worried about this particular concept. Let's see how it is. Before that, let me present a quote by a mathematician named John Mason in his paper about abstraction. Generalization or abstraction is the heartbeat of mathematics. If teachers are unaware of its presence and are not in a habit of getting students to work at expressing their own generalizations, then mathematical thinking is not taking place. What we have done in this particular definition is we have looked at the real world idea of distance which each of us are familiar with, and we have tried to write it in a language which is the most beautiful language on earth, called mathematics. Some quotes say mathematics is a language with which God wrote universe. That's because there is no language like mathematics which is precise enough to express ideas well and precisely. So this is nothing but the idea of distances which we already know in mathematical terms. Let's see how it is. The intuitive idea of distances versus mathematical formulation. To begin with, if I stand at the same point x and I do not move, I have traveled zero distance. This rho of x comma x is equal to 0. Let me read it in another way. Distance from x to itself is equal to 0. Before we continue, let me make a small note. Here, we are rewriting something real world in mathematical terms. And when we are doing it, we will take the simplest model possible. For example, suppose there are 2 points x and y. You can go from x to y in whichever way possible. You can walk zigzag, take left, right, left, and take a sequence of left and rights and reach y, or you can walk straight from x to y. Since we are making a mathematical model here, or we are trying to abstract it, we'll take the simplest case where when we say distance between x and y, it is a straight line distance between x and y. So let's look at the second condition. It says rho of x comma y is greater than 0, which when x is not equal to y. It's highly intuitive, right? Given x and y, movement, if someone is walking, suppose Kezia is walking from x to y, and definitely the distance she traveled is going to be a positive distance. Now, even if I am walking backwards, I can only travel a positive distance. So, second condition turns out is also something inspired from distance. Now, the third condition is also easy. If you notice, it said rho of x comma y, flip the input, rho of y comma x, the value given by this function will be the same. In the real world, we know that if you take a picture and if you flip it, if it gives the same idea, same image, we will call it a symmetric picture. And we mathematicians are obsessed with symmetry. And this is nothing but the idea of symmetry that is there in the idea of distances. Suppose I'm going from x to y, and suppose Indra is going from y to x backwards. Since we are traveling in straight line, both of us would have traveled the same distance. Distance from x to y will be equal to distance from y to x. Now, about understanding the definition, there is something that we have to see. Here, we'll take a hint from the fourth condition here, which says triangle inequality. It is called triangle inequality. So it has something to do with triangle, it seems. And let's try see what it means. Suppose there are 3 points x, y, and z. And obviously distance, as I already told you, is about straight line distance between 2 points. Going from x to y, we already noticed that there is one way of walking straight. And imagine someone was very curious to know what happens if what is happening in z. So uh, one person decides to walk from x to y straight. Another person decides to go to x to z and then see what's happening in z and then go from z to y. It is highly intuitive that going from x to y straight was the shortest distance compared to going from x to z and then from z to y. That's exactly what is written here in triangle inequality. Rho of x comma y is less than or equal to rho of x comma z plus rho of z comma y. Now let me reread it in this way. Straight line distance from x to y is less than or equal to straight line distance from x to z going from x to z and then from z to y. It is trivial that if you look at the image, there is a triangle formed, and that's why this particular condition is called triangle inequality. Now, turns out things are falling in place. Intuitive idea of distance has matched with mathematical formulation. But there's a small question. Here we have rho of x comma y less than or equal to. In this case, if you notice, going from x to y and going from x to z and z to y is always going to be less than condition, strictly less than condition. Then why do we have less than or equal to here? Now, we'll take a 2-minute break. You can review the concepts which are presented to you. Many of you may be familiar with it already. For many of you, this may be the first time you're hearing it. Many of my students are here who has heard this class and live in classroom. So take a moment to go through the concepts which are presented. Meanwhile, leave your thoughts on why that less than or equal to is there instead of strictly less than. Yes, Bijal, that's true. If x and y are collinear, what does it mean by saying collinear? Which is basic geometry to say that if x, y, and z are in the straight line. So take a minute off, think about whatever we have discussed so far, because we are going to enter into examples and counterexamples and challenges. And in this entire section, and in all these sections, we'll be using these concepts as our reference point. So do not by heart the condition, but understand the essence of each of these conditions. Now, let me repeat, do not hesitate to leave a chat here if you have any doubts. I am open, I can address it straight away before we proceed. So feel free to just point out whatever doubts you have, feel free to just point out straight away out here. I can address it before I proceed. Anyway, let's continue. So as Bijal said, if they are collinear, that is x, y, and z lie on the same line, what happens is going from x to y straight is equivalent to saying I'm going from x to z and then from z to y. In that case, rho of x comma y will be equal to rho of x comma z plus rho of z comma y. So notice how we understood the definition right now. We looked at the definition, and then we looked at how could this idea possibly be born. Is there any idea that I know in real world which is similar to this definition? And turns out it was nothing but the idea of distances. So that's one part about understanding definitions. Look at what you have in your hand and try to connect it with what you have in real world. People always ask, how do you apply real analysis? Why do we even study real analysis? How do you apply it in real world? In fact, real analysis is one of the fields of mathematics which is most applied in real world. But we don't realize that because most of the times in our classrooms, we forget to connect it with the real world. We just simply talk about the mathematics of it and walk off. Now, let's continue to a few examples, and turns out most of it you're already familiar with. Before I proceed, let me point this out. How will examples and counterexamples help? Examples and counterexamples, as you would see in following slides, would help you understand a definition or a concept better. 2. Almost all the entrance examinations that you write and post your real analysis classes or colleges, all you have to do is to apply a concept to see whether something fits in a particular description or not. When you're doing that, all you need to know is to check whether a fact is true or false. Sometimes examples and counterexamples help us solve the problem in our hand faster. For example, let's talk about it in the entrance examination perspective. CSIR-NET or JAM or GATE or whatever it is. Objective type questions are followed there, and in objective type questions, there is one thing for sure. There are 4 options in almost all exams, and out of those 4, at least one of them is true for sure. Your job is in selecting those which are true or rejecting those which are wrong. And in exam, you're going to be tested on how fast you can do it. It's about how fast can you select those which are true, or how fast you can select those which are false. So sometimes you can directly solve it from the facts given in the question, or sometimes you can take advantage of the fact that it's objective type. My friend Christy Vergas and I, when he was starting to write the book, we focused a lot throughout the book, CSIR-NET General Aptitude, a New Outlook. We focused a lot on rewriting the content in such a way that we teach you how to solve a question, looking at an objective type question and taking advantage of it. And in mathematics especially, you can do that better. Sometimes a question will be solved faster using an example or a counterexample rather than direct solution. So it's important that you should know how to apply example and counterexample in a given question. 1. 2. It's important that you have a good collection of example and counterexamples with you before you go for the exam. For example, the problem is constructing examples and counterexamples in mathematics is not easy. So if you have a good collection with you already, you can always try to manipulate it. You can always try to use those examples, or using those examples, you can construct new examples which will help you solve the question faster. We'll see how it is how it is done in the future sessions. Anyway, let's proceed. First one is trivial. All of you have discussed it in your school, colleges, everywhere. So I'm not going to go in detail about it. In real line, that is R, you have distance between 2 numbers. That is, let's take 3 and 6 as quoted here. Distance between 3 and 6 is 3, not minus 3. But 3 minus 6 is always minus 3. But distance between 3 and 6 is 3, not minus 3. Have you ever wondered how it is? That's because the metric governing, or the metric which we apply with R in this case, is rho of rho is a function from R cross R to R. Notice that the domain matches and codomain is R. We don't know about the range yet. Rho of x comma y is equal to absolute value of x minus y. We know that absolute value of a real number, x minus y will be a real number again, and absolute value of x minus y will be a non-negative real number. So definitely we can be sure that rho of x comma y, or this function rho, has range closed interval 0 comma infinity. Now let's look at the other conditions. 1. Rho of x comma x is equal to absolute value of x minus x is equal to 0. Trivial. X minus y will always be a real number. Absolute value of real number will always be positive number. Now for the third condition, we are going to use a simple property of absolute value, that absolute value of xy is less than or equal to, absolute value of xy is equal to absolute value of x into absolute value of y. So rho of x comma y is equal to absolute value of x minus y is equal to minus of y minus x. I am taking a minus out from x minus y, and I am using the property to split it. Absolute value of minus 1 is 1, disappears, and you're left with rho of y comma x. Now again, for the fourth property, triangle inequality, I am going to use another property of absolute value, rho of x comma y. The property that I'm going to use is the inequality that absolute value of x plus y is less than or equal to absolute value of x plus absolute value of y. So rho of x comma y is equal to rho of x absolute value of x minus y, and I'm going to use a trick which you would have seen in real analysis from the first day of analysis class. The trick is something simple, adding a 0. Absolute value of x plus 0 minus y will be equal to absolute value of x minus y. Now this plus 0, I'm going to rewrite it as minus z plus z. And then I'll use the inequality which I talked about earlier to split it and get rho of x comma y is less than or equal to rho of x comma z plus rho of z comma y. I'm not going to delve into details of this. If you have any doubts so far, leave a comment right now. Welcome, Kritika. We have talked about definition of metric spaces, and we are just looking at the example, the first example that we learned in our class called absolute value distance on R. So this metric has different names. One, it's called absolute value metric, or it's also called Euclidean metric on R. And fact that this is the metric that we use in our real world everywhere, this is also called usual metric on R. Now, simple questions. My students who are here are familiar with me in the class, always telling them that mathematicians are superhumans. That's because we literally are superhumans. We do things that physicists will take another 100 years maybe to solve. We solve problems and get things ready for physicists which would take forever for them to solve. Imagine a world where teleportation was possible. Those who are Harry Potter fans, you would notice that there is a way in which Harry Potter would think about a place and they go to that place. So like that's called teleportation in real world, and scientists have been burning their head to make teleportation machines in real world for many years now. Now it's been hundreds of years of research and they were not able to do it, but turns out we have set the mathematics for it set and ready. By the idea of teleportation, what I mean is to go from anywhere in this world to anywhere else. It takes 1 unit of distance. I'm saying 1 unit because it's not 1 kilometer. It may be 1 second, it may be 1 nanosecond. We don't know what it is. I'm just generally going to say 1 unit of distance. In that case, Turns out we can define a metric on R that will help us understand that world better. Consider R along with a metric D from D from R cross R to 0 comma close set 0 comma 1. Notice a couple of things. One, here codomain is 0 comma 1 set. 2, it is not equal to closed interval 0 comma infinity. It's a subset of closed interval 0 comma infinity. But our definition was very careful in wording it that the range should be contained in closed interval 0 comma 1. And turns out here this codomain is contained in closed interval 0 comma infinity. Hence this D works. Now this D is defined as d of x comma y is equal to 0 if x is equal to y, 1 if x is not equal to y. As I told you, domain R cross R. The D is a metric on R. Range closed interval 0 comma 1, and those are the only two values this particular metric the function takes, and it's a subset of closed interval 0 comma infinity. Problem solved. The first three conditions are trivial, because if x is equal to y, d of x comma y is equal to 0. If x is not equal to y, d of x comma y is equal to 1 greater than 0. Third condition, d of x comma y will be equal to d of y comma x, because if x is equal to y, it's 0, and if it's not equal to y, it's 1. So first three conditions are trivially satisfied. Let's talk about the third condition, which is triangle inequality. Now, triangle inequality is not too direct, but we can solve it in two simple cases. First case, when x is equal to y, d of x comma y will be equal to 0, which is less than or equal to d of x comma z plus d of z comma y, because d of x comma z can take either 0 or 1. D of z comma y can also take either 0 or 1. Hence, in right hand side, the possible values are 0, 1 and 2. Definitely 0 is less than or equal to all three numbers. In the second case, you have x not equal to y. Then d of x comma y will be equal to 1. So in this case, there are three subcases. 1, if x is equal to z, then x is not equal to y, hence z is not equal to y. So d of x comma z will be equal to 0, d of y comma z will be equal to 1. Hence 1 is less than or equal to 1. Or if y is equal to z, since x is not equal to y, x is not equal to z. Same case repeats. Or if x is not equal to y is not equal to z, then we will have 1 less than or equal to 2. These are the classic examples which are followed in the class. So I am not going to get into more details of it. But anyway, if you're making notes of what we are discussing here, make a note of these things quickly. So this particular metric is called, how do we get equal to 0 in the first case? So yes, Bijal. So d of x comma y, here in the first case we are considering x is equal to y. When x is equal to y, by definition of our metric here. Oh yeah. That's why I told you in the first case LHS is 0. In RHS it can be 0 or 1. 0 or 2. 0 or 2. Because suppose x is not equal, z is not equal to x, then z is not equal to y. D of x comma z will be 1 plus d of z comma y will be 1. Hence 1 plus 1, 2. So LHS will be 0, RHS will be, yes, that's true, Bijal. Yes. So when x is equal to y is equal to z, RHS can be 0. But in either case, turns out 0 is less than or equal to 0 or 0 is less than or equal to 2. Is it clear, Bijay? Can we proceed? So this metric is called discrete metric on R. And as I told you, if we could go from anywhere to anywhere at any point of time, that is, if teleportation was possible, turns out we have defined the distance in such a world. And using this distance, we have further studied what does open set mean in this world? What does uh, continuity mean in this world? And turns out this is a very interesting example because soon we will define continuity, but still a spoiler for you. In this world, every function will be continuous. That is, give any functions that you like, it will be continuous in this world. Those which are discontinuous in R with absolute value metric or the real functions, they will also be continuous here. So this world is a lot interesting to us because things are very smooth here. We will see about it soon when we discuss other definitions like continuity. But the reason I discussed it is sometimes in few exams, few CSIR-NET and other exam questions, this example helps us a lot to cancel out or reject many wrong options. Anyway, let's make some observations from what we have observed so far. We notice that on the set R real numbers, we have defined two metrics. One is absolute value metric and another is discrete metric. And turns out same set can have more than one metric. Notice what we are doing. We are not going for any textbook to find out properties, or we are not going to any textbook to generalize some properties. We are just observing. We just looked at some examples and turned out, oh, there is something interesting. Same set can have two metrics. So we have understood something better about the definition we are learning right now. And then let's look at another one. Same set, the same metric may work on multiple sets. For example, absolute value metric that we talked about will work on R, which works on R, will also work on a set M is equal to closed interval 0, 1. The same metric may work on different sets. See that we didn't touch any textbooks. We just looked at some examples. From those examples, we are understanding better things, properties of the definition object we defined in this definition. Let's make one more observation. We can find a metric on any given non-empty set. I just wanted to catch your attention, so I put two smileys, a smiling and one sad face, and I've defined a metric on it. Turns out it satisfies all the properties. In fact, you will see that this is similar to the discrete metric we defined on R, and turns out discrete metric works on this set M as well as the set R. So again, emphasizing on the previous observation that same metric may work on two sets, and I'm being careful in saying same metric may work on two different sets. Some metrics will work on some sets and it will not work on other sets. We will see that once we reach counterexamples. In the counterexamples, we will see that some metrics which work on a particular set need not work on another set. So depending on time, we'll do it today. If not, we'll get to it in one of the future classes. So I'll give you another 2 minutes to quickly recollect whatever we discussed so far. And if you have any doubts, feel free to ask right now before we get to counterexamples. That's an interesting question, Nigida. Nigida just asked if there are any metrics which work on every set. Mm, there is one, and I'm not going to give you the answer because you have been my student, so you know how I always make you run around for a simple question. So there is one, and can anyone think of that particular metric which may possibly work on more than one set, as in every possible set? Welcome, Balakrishnan. We are halfway the session, and these are the things we have discussed so far. We have talked about definition. We have talked about where it came from. We talked about a few examples and some properties. So, can you think of others who have been here? Can you think of a metric which can possibly work on any given set? Uh, so the it will be worth noticing that I have already mentioned that particular metric, which can possibly work on any given set. That's nothing but the discrete metric. Just try to figure out how discrete metric works on any given set. Yes, Bijal, that's true. So, yeah, Nikita, there is a small problem with Euclidean metric. Euclidean metric is defined for R and it works on R. It is real numbers. So, as Bijal pointed out, discrete metric works for any set. And in fact, if you notice in terms of topological spaces, those who study topology would know, discrete metric, the topology of discrete metric is nothing but the power set of X. Hence, every set has a power set, and it's easy to conclude that it will work on every set given. Yes, Vijay, I had switched it off for a second just to check something. Is it clear? Is there any other questions? So to conclude, there was a question by Nigida whether there is a there is a metric which works on every set possible. So there is one, and it is discrete metric, which we already talked about earlier, and it works on every single set possible, which are non-empty. Now, Nikita had another doubt if Euclidean metric will work on every set. Metric will work on every uh, real numbers and its Cartesian products, r square, r cube, r to the power n, all of them. You can generalize Euclidean metric to work on each of these sets. So can we continue? Now let's quickly recap. We talked about definition of metric spaces. Where did it come from? We talked about the idea of abstraction, and I'm going to emphasize on it again. The pure joy in learning real analysis or any pure paper is understanding how they have abstracted a concept, how they have tried to bring out a real world concept and tried to put it in mathematical terms. And you should be focusing, as a mathematics student, you should be focusing on learning to abstract yourself. So, and then we looked at two examples, absolute value metric and discrete metric on R. Two, we made some observations. That is, one set may have different metrics. Same metric may work on different sets. We can find metric on any given non-empty set. And I must also add, emphasizing on the third point here, same metric may work on different sets. Discrete metric may work on any given set. And thank you, Nigida, for pointing it out. That's some good mathematical thinking. Now, let's get to the next section. I believe I can go through a couple of counterexamples before we wind up today. Welcome, Praveen. I believe I can. I don't think I'll have enough time to go through all the counterexamples today because I will wind up by 12 o'clock. So counterexamples, much like examples, helps us understand concepts better. So let's get to it. I've given the definition to the right so that it's easier for us to refer to. And I hope by now you are all intuitively clear about this definition. Consider any set M. Now, a function given by rho from M to closed interval 0, infinity cannot be a metric on M. I've given the reason here, I should have hidden it actually. So, why is it so? Because the definition says there are 6 conditions, there are not 4, there are 6 conditions to be satisfied in the definition. 1. The first one says the domain of this particular function rho should be M cross M, and here it is simply M. Hence this particular rho cannot be a metric on the set M. Now notice that it is something trivial that they wouldn't point out anywhere, but it is help us. This particular counterexample is helping us understand key words in definition. Why is this definition worded so? What is the importance of each word in this definition? That takes me to another point. We know that our teachers always tell us to by heart the definition word to word, don't miss a word. Unfortunately, for those who studied under me, they will know that I would not force them to do so. The reason is every word matters, and sometimes as a student who is introduced to a definition for the first time, we might not understand the definition completely, and when we write definition on our own, we may miss one or two key concepts in it. And these, through the counterexamples, that's what I'm going to point out. The things which you will consider to be not so relevant and give. Yes, Vigil, that's true. We need pair of elements. We can't take one element alone and define a metric. And also the definition demands that domain should be M cross N. So turns out, no, here when our domain is M, it's just going to be one number X. So row of X doesn't make a meaning to say distance. So that's why the definition clearly demands that domain should be M cross M. So I would always encourage you to do one thing. Once a session is over, you can read through this definition once more. Try to understand the definition. Try to write it again in your own words. Mathematical part of these 4 conditions, you might have to repeat it as it is. But other parts which is explained in English, try to write it in your own words. You can send it across through any of the channels which are mentioned above, or you can always chat here in the next session. You can point out your doubt before we start the session, so we can discuss it and continue. Now try to write the definition on your own and see how correct you are if you missed any important points, so that you train yourself to frame an intuitive idea in your mind into mathematical terms. And that's the pure joy of mathematics, where you're enjoying mathematics rather than by hearting something which is pointless. You're creating mathematics, you're learning how to create mathematics. There's a definition which is already existing, but when you're trying to do it yourself, you're actually learning how this definition was worded. Later, when you come across a new idea yourself, you'll be able to express it yourself. Let's look at the second counterexample. If A is a proper subset of M, any proper subset, a metric, a function given by rho 1 from A cross M to 0, closed interval 0, infinity. cannot be a metric on M or A. The reason again is emphasizing on the fact that domain should be M cross M. So here if you notice, suppose we are considering subset closed interval 0, 1 of A is equal to closed interval 0, 1 and M is equal to R. Then the metric should be defined on any given number in M, right? So what if I ask you, the numbers of A cross M will be of the form 0, 2, 0, 6 or 0.5, 2, etc. So the question is, what will be the value of 2, 2, row of 2, 2? We won't have an answer. And that's why this will not be a metric on R or A. So the domain, I'm emphasizing on the fact that domain should be M cross M. Now, third counterexample. Consider any set M with 2 or more elements. I'm giving a small condition here. M should have 2 or more elements. A function given by row from M cross M to 0, set 0, cannot be a metric. The reason, but notice that our conditions are satisfied. 1, domain is M cross M, range is contained in closed interval 0, infinity. Range is contained, so range is singleton 0, which is contained in closed interval 0, infinity. So this cannot be a metric on M, as the reason is row of x, y. Since there are 2 or more elements, suppose x is not equal to y. Since there are 2 or more elements, row of x, y can only be equal to 0 because that's the only value in codomain. Hence, it doesn't satisfy our second condition here. So this particular function cannot be a metric on M with 2 or more elements. But then there is a simple question. What if M has only one value? That is, M is a singleton set. Will this particular metric work? Leave your thoughts in the comment. The question is, what if M is a singleton set? Here in this particular counterexample, I said it should have 2 or more elements. What if M is a singleton set? In that case, would this particular metric function work as a metric? That's right, Bijal. In that case, it works easily because there is only one number. Since there is only one number, we can, excuse me for a second, yeah. Since there is only one number, and since there is only one number, row of x, x is the only possible value you can put into the function row. Hence, it works as a metric. Yes, Jocelyn and Bijal, you are correct. So, notice that what we did here is, we noticed a counterexample. From that, there was a particular extra condition given that 2 or more elements. Next thing we did is not stop with understanding we got from this particular counterexample. We extended our question. We asked a question to this counterexample. Why are you saying it's 2 or more elements? What happens if it's less than that? Less than that, the only possibility in number of elements is 0 elements or 1 element. 0 is not allowed. Why? Why is 0 elements not allowed in M? Because I have trimmed the definition a bit here, but initially when we defined it, we said M should be non-empty. So 0 is not allowed. The only possibility is 1. When it's 1, as we already said, row of x, x is the only possibility, equal to 0, and it works as a metric. Now let's look at another counterexample. We'll hopefully wind up with this particular counterexample, and there are a couple more counterexamples, 4 or 5 more counterexamples, which we will continue in the next class. Now, consider any non-empty set M, a function given by rho from m cross m to 0 comma infinity, open interval 0 comma infinity, cannot be a metric on M. Notice that 1, domain is fixed m cross m, and range is contained in 0 comma closed interval 0 comma infinity, true, and those two conditions are satisfied. But then, which of these 4 numbered conditions does it fail? You can easily see that rho of x comma y has to be equal to 0 for the first condition. That means 0 should be there in our codomain or range. And turns out for this particular condition, 0 is not there in our codomain. Hence, first condition cannot be true, will not be true at any cost. Welcome, Navya. So, this particular counterexample will not work for any given set M. Now, if you have any doubts in whatever we discussed so far, you can use the next 5 minutes to ask them. Or if you have any observations that you have made from what we discussed so far, please feel free to ask them right now. Have you ever thought definition in detail like this? Most of the times when I ask my students the definition of metric spaces, they'll simply list the 4 listed properties here: rho of x comma x is equal to 0, those 4 things, right? No, it's not. The entire definition is carefully worded, and all the facts given in it are equally important. So this is the power of definitions. There are a lot of things to understand about a definition. It's like how the blind went to see the elephant. There were 4 or 5 blind who went to see the elephant, and some touched the legs, some touched the tail, some touched the nose of the elephant. And at the end of the day, one said elephants is so hairy, and another said elephant is as big as a pillar, and another said, oh, it's so long and small. So what I am saying is, there is a lot of things to understand about a definition. As a graduate or a undergraduate or a postgraduate student, or someone who has finished it, we can never stop understanding a definition. I still enjoy simple definitions and analysis for hours together.